Open Shortest Path First, OSPF, functions as a routing protocol within Internet Protocol, IP, networks, operating as an Interior Gateway Protocol, IGP, in a single autonomous system, AS. Using a link state routing, LSR algorithm, OSPF collects information about network links from routers, creating a network topology map. This map serves as a routing table for the Internet layer to direct packets based on their destination IP addresses. OSPF is compatible with both IPv4 and IPv6 networks and is a prevalent choice in large enterprise networks. In contrast, ICIS, a similar LSR-based protocol, is more commonly employed in large service provider networks. Originally conceptualized in the 1980s, OSPF version 2 is detailed in RFC 2328, 1998, while the specifications for IPv6 are outlined in OSPF version 3 in RFC 5340, 2008. Furthermore, OSPF accommodates the classless interdomain routing, CDAR, addressing model. OSPF functions as an Interior Gateway Protocol, IGP, facilitating the transmission of IP packets within a specific routing domain like an autonomous system. Through collecting link state details from connected routers, OSPF builds a network topology map, which is then translated into a routing table. This routing table assists the Internet layer in forwarding packets based on their destination IP addresses exclusively. Noteworthy is OSPF's ability to swiftly detect network topology alterations, such as link failures, and promptly converge towards establishing a new routing structure, free of loops. The mechanism behind OSPF's computation of the shortest path tree for each route is rooted in a technique closely aligned with Dijkstra's algorithm. Routing decisions within OSPF are steered by link metrics tied to individual routing interfaces, which might include factors like round-trip time, data throughput, or link reliability expressed through numerical values. This approach fosters a fluid process of distributing traffic load evenly among routes of equivalent cost. Administratively, OSPF simplifies network management and enhances resource utilization by segmenting the network into distinct routing areas. These areas, designated by 32-bit numbers, are often represented in decimal or dot decimal notation akin to IPv4 addresses. Typically, Area 0 serves as the core or backbone region within an OSPF network, while other areas must be connected to this backbone through an Area Border Router, ABR. ABRs manage separate link state databases for each area, maintaining summarized routes for the entire network. Unlike some routing protocols, OSPF does not rely on a transport protocol like UDP or TCP, but encapsulates its data directly into IP packets tagged with protocol number 89. OSPF leverages multicast addressing to disseminate route information within broadcast domains, utilizing specific multicast addresses to facilitate this process. The protocol also includes provisions for neighbor discovery in non-broadcast networks. Notably, OSPF multicast IP packets are restricted to a single hop and are not routed across multiple IP routers. While OSPF operates over both IPv4 and IPv6, it implements its transport error detection and correction functions and employs multicast addressing for information sharing within broadcast domains. OSPF also offers a virtual link feature enabling the creation of adjacency tunnels over multiple hops. Security-wise, OSPF over IPv4 can incorporate various authentication methods to restrict participation to trusted routers, while OSPF v3 for IPv6 relies on standard IPsec for security without internal authentication means. Furthermore, OSPF supports the Multicast Open Shortest Path First, MOSPF protocol for routing IP multicast traffic, although it is not included in Cisco's OSPF implementations. Additionally, OSPF version 3 brings modifications to the IPv6 implementation of the protocol, including the utilization of IPv6 link local addressing exclusively for neighbor exchanges. These exchanges happen per link rather than based on subnets, and OSPF v3 has made strides towards being protocol independent by eliminating IP prefix information from its advertisements and Hello Discovery packets. Point-to-point P2P, broadcast, non-broadcast multi-access, NBMA, point-to-multipoint, and point-to-multipoint non-broadcast, P2MP-NB, are the different network types discussed in the document. For point-to-point and broadcast network types, an unlimited number of routers per network are supported. Non-broadcast multi-access (NBMA) networks and point-to-multipoint networks also allow an unlimited number of routers per network. Point-to-multipoint non-broadcast networks support up to 2 routers per network. The full mesh assumption is present in point-to-point, broadcast, and non-broadcast multi-access (NBMA) networks, but not in point-to-multipoint or point-to-multipoint non-broadcast networks. The hello timer is set to 10 seconds by default in Cisco networks, while the dead timer is set to 40 seconds by default. The wait timer is set to 0 in point-to-multipoint and point-to-multipoint non-broadcast networks, and equal to the dead timer in point-to-point, broadcast, and non-broadcast multi-access networks. Automatic neighbor discovery is enabled in point-to-point, broadcast, and point-to-multipoint networks, but not in non-broadcast multi-access, NBMA, or point-to-multipoint non-broadcast networks. In the case of discovery and hellos being sent, they are directed to 224.0.5 for all network types. Neighbor communication is sent as unicast for all network types, except for the non-broadcast multi-access NBMA network type, where it is sent to the neighbor IP. LSAs are sent to 224.0.5 for point-to-point, broadcast, point-to-multipoint, and point-to-multipoint non-broadcast networks. DR-BDR communications are directed to 224.6 in point-to-point, broadcast networks, and to 224.5 in point-to-multipoint and point-to-multipoint non-broadcast networks. Next hop IP is directed to the peer for point-to-point, original router for broadcast, non-broadcast multi-access, and point-to-multipoint networks, and to the hub for point-to-multipoint non-broadcast networks. When imported into OSPF, the network types are distinguished as stub and P2P for point-to-point and broadcast networks, transit for non-broadcast multi-access and point-to-multipoint networks, and stub for point-to-multipoint non-broadcast networks. OSPF employs both unicast and multicast transmission modes to disseminate hello packets and link state updates. As a link state routing protocol, OSPF creates and maintains neighbor relationships to exchange routing updates with other routers. The table storing neighbor relationship information is known as an adjacency database. For 2 routers to be considered neighbors, they must share the same subnet, area ID, subnet mask, timers, and authentication. OSPF neighbors establish a connection to recognize and comprehend each other, with hello packets being the only information exchanged. No routing information is shared at this stage. Adjacencies in OSPF are formed between selected neighbors to facilitate the exchange of routing details. 2 routers must first become neighbors before progressing to become adjacent. Routers achieve adjacency status if at least one of them is a designated router or backup designated router on multi-access networks, or if they are linked by a point-to-point or point-to-multipoint network type. To form a neighbor relationship, the interfaces involved must belong to the same OSPF area. Although interfaces can be configured to be part of multiple areas, this practice is generally avoided. OSPF can operate in various modes depending on the network setup, such as point-to-point, broadcast, non-broadcast multi-access, point-to-multipoint, and passive. Additionally, OSPF supports indirect connections like virtual links, including tunneling and sham links, which traverse the routing engine rather than a direct link to the remote host. The adjacency state machine in OSPF manages communication between routers to establish and maintain adjacencies through a series of defined states, from down to attempt, init, two-way, and various database exchange phases like exchange, loading, and full state. In OSPF, neighbor adjacencies form dynamically in broadcast multiple access networks using multicast hello packets, while in non-broadcast networks, adjacencies are established through unicast packets. Passive networks advertise without initiating neighbor adjacencies, and non-broadcast networks like X.25 public data networks, WireGuard, and serial interfaces require direct communication between routers to elect a designated router, enabling the generation of link state advertisements, LSAs, for the network's operation. The network is partitioned into OSPF areas to group hosts and networks logically. Each area is linked to a router with an interface for each connected network link. Routers maintain separate link state databases for their respective area, which can be summarized by the connecting router for the rest of the network. This design ensures that the topology of an area remains unknown beyond its boundaries, reducing routing traffic within the autonomous system. OSPF can manage numerous routers with potential concerns about the capacity of the forwarding information base, FIB, table in networks with extensive routes and lower-end devices. Modern low-end routers are equipped with a sizable amount of RAM, typically a full gigabyte, enabling them to support multiple routers in Area 0. Areas are uniquely identified by 32-bit numbers written in dot decimal notation, similar to IPv4 addressing. These identifiers are distinct from IP addresses and can be duplicated without conflict with any IPv4 address. For IPv6 implementations, OSPF v3, 32-bit identifiers written in the same notation are used. While most implementations expand Area 1 to the area identifier 0.0.0.1 when dotted formatting is omitted, some may expand it as 1.00.0.0. Various vendors implement features like Totally Stubby and NSSA Totally Stubby areas for different types of OSPF areas. Even though these features are not covered by RFC standards, they are widely considered standard in OSPF implementations. OSPF defines different area types such as backbone, non-backbone, regular, stub, totally stubby, not so stubby, totally not so stubby, and transit backbone area. The backbone area, also known as Area 0 or Area 0.0.0.0, serves as the central core of an OSPF network, connecting all other areas directly or through intermediary routers to prevent routing loops. Inter-area routing occurs via routers linked to the backbone area and their respective associated areas, forming the structural basis for the OSPF domain. All OSPF areas must connect to the backbone area, either directly or through virtual links. A transit area allows routing between non-backbone areas and the backbone area. A regular area, which can generate and receive summary and external link state advertisements, LSAs, is a non-backbone area without specific features. A stub area solely relies on a default route for routing within the area and does not accept external route advertisements. Modifications like totally stubby and not so stubby areas have been introduced by vendors to enhance OSPF functionality. A totally stubby area operates similarly to a stub area, but does not allow summary routes and external routes, simplifying routing decisions and reducing system resource utilization. Conversely, an NSSA permits importing external routes in a limited manner while still maintaining the characteristics of a stub area. The totally not so stubby area combines the attributes of both totally stubby and not so stubby areas, accommodating specific routing scenarios. Redistribution into an NSSA area results in the creation of a special LSA known as Type 7, which can only exist in an NSSA area. This LSA is generated by an NSSA ASBR and translated into a Type 5 LSA by an NSSA ABR router for propagation within the OSPF domain. Careful design considerations are essential when configuring a totally stubby NSSA area to ensure optimal routing performance and network efficiency. OSPF categorizes routers into distinct types: internal router, IR, area border router, ABR, backbone router, BR, and autonomous system boundary router, ASBR. An internal router has all its interfaces within the same area, while an area border router links one or more areas to the main backbone network and maintains separate link state databases for each connected area. Backbone routers have interfaces connected to the backbone area and may also function as ABRs. ASBRs, on the other hand, exchange routing information with routers from other autonomous systems and are crucial for distributing external routes within their own system. Routers in OSPF are identified through customarily written identifiers in dotted decimal format, typically mirroring an IP address. This identifier is vital for each OSPF instance and can be automatically set as the highest IP address to avoid routing conflicts. In non-point-to-point networks with various types like broadcast, non-broadcast, and multi-access, NBMA, the system of designated router, DR, and backup designated router, BDR, minimizes network traffic by consolidating routing updates through multicast addresses. DRs and BDRs maintain a complete topology table of the network and disseminate updates to other routers in the segment via multicast addresses. This streamlined approach fosters leader-follower relationships within multi-access network segments, ensuring efficient routing updates and reduced network load. These designated routers are essential for broadcast and certain NBMA networks, but are not elected on point-to-point links to avoid redundancy in optimizing bandwidth. The process of DR election follows specific criteria based on priority settings of OSPF routers and ensures seamless operation in case of failures or replacements. Routing update flow revolves around DRs sending link state updates, LSU, to multicast addresses, with BDRs and other routers responding with acknowledgments accordingly. This orchestrated communication flow ensures the synchronized exchange of routing information across OSPF networks. OSPF, unlike other routing protocols, operates without relying on a transport protocol like UDP or TCP, directly forming IP datagrams using protocol number 89 in the IP protocol field. It defines 5 message types for various communication purposes: hello, database description, link state request, link state update, and link state acknowledgement. Hello packets serve as a way for routers to greet each other, establishing relationships and sharing key operational parameters within an autonomous system or area. These messages are exchanged periodically to maintain connectivity, with a dead interval triggering a neighbor link down assumption if no hello messages are received within a certain time frame. Database description messages convey the topology of the network, sharing contents of the link state database, LSDB, between routers. The transmission of large LSDBs can require multiple messages, with a leader device sending information in sequence and the recipient acknowledging them. Link state request messages are used to solicit updated information about specific parts of the LSDB, specifying the links for which the requesting router needs fresh data. Link state update messages contain updated link information, responding to requests and circulating vital data to update LSDBs across routers. Link state acknowledgement messages ensure reliability by confirming receipt of link state update messages. OSP formulates various types of link state advertisements, such as router LSAs, network LSAs, summary LSAs, ASBR summary, AS external LSAs, NSSA external LSAs, link LSAs, and intra-area prefix LSAs, each serving distinct purposes in conveying routing information. These advertisements inform routers about network connectivity, summarizing routes, and exchanging external route details. Different OSPF area types accept specific LSAs based on their designated functions, like router, network, external, network summary, ASBR summary, and more, contributing to efficient routing within and across networks based on designated areas. OSPF utilizes path cost as its fundamental routing metric, providing flexibility for network designers to select a metric aligned with their design objectives. The cost is calculated by dividing the reference bandwidth by the interface speed and can be manually overridden. This allows for the comparison of speeds and adapts to various interface configurations. In the context of OSPF, the path cost serves as a crucial factor in determining the optimal route for data transmission across network devices. The routing metric or cost calculation varies based on the interface speed, with different types of LSAs having specific size fields for cost allocation. It's important to note that OSPF operates as a Layer 3 protocol, influencing how data packets are transmitted across interconnected networks. Issues can arise if there is a Layer 2 switch between devices running OSPF, potentially leading to asymmetric routing paths, resulting in unintended network consequences. Comparing metrics directly is feasible only when they belong to the same category, which helps maintain routing efficiency and data packet optimization across varied network architectures. With OSPF version 3, significant modifications have been introduced to enhance the protocol's functionality in IPv4 environments. Notably, OSPF v3 removes IP prefix information from LSAs and hello discovery packets, ensuring greater protocol independence. The protocol now supports IPv6 link local addressing and offers distinct flooding scopes for LSAs, enabling more efficient data transmission and routing within different network domains. Furthermore, OSPF can be integrated with MPLS VPNs to streamline routing processes for service providers and customers. This integration allows OSPF routes to retain their original LSA type and metric, reducing the need for additional tunnels and enhancing network scalability. Moreover, extensions like OSPF-TE enhance traffic engineering capabilities, enabling more detailed topology information exchange and usage on non-IP networks like optical networks.